your own SRs. If they are busy, then we will start first without them first. Otherwise, we will keep waiting and waiting. Huh? Okay, anyway, since we are waiting, anyway, I saw Li Hong and Wei Liang here. Li Hong and Wei Liang, so far, how are you all following the tempo of the lectures? Because you all are all quite new to okay, actually, maybe you all shouldn't be very new to EBM, but I think probably in your junior residency in school, people don't really emphasize on it. How are you all following it so far? Or is it too much of a content for all of you?
I think so far okay for me.
So, as in, whenever whatever we discuss, right, are those main points. A lot of times what you are going to learn here may not really just stick in. So you all need to go back and read okay, about this yourself. But these are the main points that we have highlighted based on your seniors before, that we think are important to know, so that when you read papers later on, presenting for a journal club or preparing for exam, at least you already had some background knowledge and you already start reading all these concepts, so it's easier for you. Okay. Okay, are we waiting for anybody else? Can anybody just tell me? I don't want to keep waiting.
Yeah, EE, I think still having clinic, and
Okay.
Valerie post call.
Okay, so no one else. I'm going to start, okay? Can? Super, I'm going to start now.
Okay.
Dr. Jennifer, I start first?
Yeah, okay, can. So, okay, please, okay, so the people who are actually presenting, please take note of the time, okay? Otherwise, we will overrun very big time. Your words are very, if your slides are very wordy, please just help to scale down in terms of the presentation.
Okay.
Okay, can we mute whoever?
And then after that, currently what? Okay, you write it first.
Sorry, I'm in a. Okay, can I start?
Yes.
Okay, so today I'll be talking about the different common statistical tests. So the few things to go through first. So how do we actually select all the appropriate statistical tests, right? There are so many different tests. Mainly the four factors to consider will be how many samples are being compared, the type of the data in the samples, the distribution of samples, and whether the data is paired or unpaired. There's a lot of all these definitions to go through, so we have to I'll go through them as clearly as I can. So the first thing will be to talk about the samples compared is quite evident from the data you get. So we'll start from the type of data. Okay, so what are the different types of data? So there are two main groups of data. I think these stats there's so many same words that are actually words that are describing the same thing. So for the first one is qualitative data. Sometimes you can see they can call it categorical or non-numerical. So basically they all mean the same thing. Basically data that does not have a number. Yeah, so qualitative or categorical data would be things like gender, marital status, color. And within this group of qualitative data, it can either be binary, so it's like one or the other, or multi-category. So binary would be things like gender, male or female. Multi-category would be like race, Chinese, Malay, Indian. Yeah. So and then the way it's measured also. So it's measured on both either a nominal or ordinal scale. So a nominal scale basically means that there's no order or relationship to each other. They're just labels like gender, hair color, religion. Ordinal scales have a certain kind of order or rank. So let's say from let's say satisfaction. So from very unsatisfied to very satisfied. Severity, from mild to moderate and severe. Yeah, so all these are part of qualitative and non-numerical data. I think for me, the easier way to know this is really just whether it's numerical or non-numerical. Okay, so the second one will be numerical data. So they can also be called quantitative. They can also be called continuous data or numerical. Yeah. So actually, they can either be discrete or continuous. Discrete means that they have a finite number of possibilities. So you talk about how number of pupils absent a day, what's the waiting time. So these are all just finite number. Continuous data is, on the other hand, have infinite possibilities. So the diameter of something, or the weight, there's a whole range and all the different possibilities. This data is measured on interval or a ratio scale. So interval scale basically does not have a fixed starting point. So things like Celsius, for temperatures for Celsius, right? So there's no zero. There's no the first start point is not zero. Zero is just a point on the scale. So there can be a negative something temperature, right? Yeah. Ratio scale on the other hand has a true zero. So things like height, weight, money, and age. So then the distribution of the data, right? So normal versus non-normal distribution. So again, for normal distribution, there's also a lot of different terms that can describe this. It can be normal, it can be called normal data, it can be called parametric data, Gaussian distribution. All these are all mean normal distribution. So a normally distributed data is perfectly symmetrical. It's a bell-shaped curve. You can summarize the data using a mean and a standard deviation. And so the central limit theorem here is very commonly used, talked about, and a central principle of normal distributed data is basically the larger the sample size, the more likely that the normal distribution exists. And in a perfect normal distribution, the mean, the median, and mode are all the same. So about non-normal distribution, right? Non-normal distribution basically is not like a bell curve. The curve is either skewed to the left or to the right, either positive or negative skew. So this, because it's skewed to one side, right? Then the median will be a better summary of the data compared to a mean, right? So the median will be the middle value. You put all the values all in a line, right? The middle values in the range, and it's used because it's less affected by the outliers compared to the mean. The disadvantage of course of using a median is that you don't take all the data into consideration, and basically how they summarize the data from either the median or interquartile range. If they take interquartile range, they will put the data into 4 different quartiles. So again, you line up the data in a row, right? So then you have the first 25%, the second 25%, and then so on and so forth. And then you take the middle 50% of the range. That's the interquartile range. So what about paired and unpaired data? So again, this is one of the key concepts in statistics, right? So a paired data is basically...
Keefe, sorry. Could I just interrupt you? So if you were to give a one-line definition of the median, because you're right, the median is the one that we most commonly use for this measure of central tendency. What would be a one-line definition of median?
Yes. Hello.
Yeah, sorry, what would be a one-line definition of the median?
What would be the one-line definition of median?
Yeah.
The middle, the 50% of...
Okay, that means that for the given value, right, 50% of all the other values lie above this and 50% lie below this value. Okay, yeah. So it is useful for most things when we are calculating the central tendency. Okay, yeah, sorry to interrupt, but that one-line definition is important because I think we use median the most of all of them. Then of course, mean was something we learned. It's just like a simple mean, right? You just add everything and divide by number of observations. And then how about mode?
Mode will be the most commonly seen
values.
Yes.
Correct. Yes, that's right. The one with the most number of people or patients or whatever having that value. Okay, sorry to interrupt. Great. Carry on. Yeah.
So I think just now I can't really hear you at the. Can you repeat the one line? Is it my connection is unstable? Sorry.
Oh, could be my connection. Okay, so the one-line definition is where for that value.
Is my connection unstable? Are you okay?
Yeah, your connection is stable. Yeah.
Okay.
From my point of view, yeah. Got it?
Okay, so paired and unpaired data, right? So paired and unpaired data basically, for paired data, it means the data that is collected from the same individual at a different time point, right? So for example, in the trial, and you want to see whether when you take the drug, how it affects the BP. So you measure the BP of the patients before taking the drug, and then you measure the BP of the same patients after they take the drug. So that will be a paired data. If it's unpaired data, you basically are comparing data from the groups with two different subjects. So for example, again, back to the blood pressure example, right? You take the blood pressure of patients under the treatment drug and compared to patients, blood pressure of patients with who are taking a placebo. So these are totally different group of patients. Therefore, they're unpaired. So another example would be like if you want to see do an experiment where you want to compare and see how drinking some energy drink can affect the heart rate, right? So the paired way to do it will, of course, to get this group of people to and measure their heart rate before they drink the energy drink, then ask them to drink the drink and then collect and measure their heart rate after. So the unpaired way would be to measure the heart rate of people before drinking the energy drink, and then measure the heart rate of another group of people who have just drank the energy drink. Yeah. So of course, in the sense that a paired way of doing it would be more accurate. Okay. So I came up with this chart to really summarize everything and help us decide what kind of tests we are going to use. So again, so from the top, there are under statistical tests. Firstly, you have to determine if what kind of data it is, whether it's a numerical or non-numerical data. So let's say if you go down the non-numerical data, so categorical, qualitative, non-numerical data, then if it's a paired data, then you just use the McNemar's test. If it's unpaired, then it depends on usually whether it's the sample is small or large. If it's a small sample, we can use a Fisher's exact test. If it's a large sample, it's a chi-squared test. For numerical data, then you see whether the data is normally distributed or non-normally distributed. If it's a normal distribution, again, then you see whether it's paired or unpaired. If it's a paired data normal distribution, then you use the paired t-test. If it's more than two groups, use the ANOVA, the analysis of variance. Similarly, if it's unpaired data and it's more than two groups, it's also the ANOVA. If it's just two groups or less, two groups, sorry, then use the unpaired t-test. Yeah, the others, this will be the non-normally distributed, then again paired or unpaired, and then based on that it will be either the Wilcoxon's match pairs, fragments test, or the Mendeleev and Kruskal-Wallis. So a t-test and an ANOVA, they usually compare the means of the samples. So again, why means, right? Because it's a normal distribution. Therefore, the most appropriate data to compare would be the mean, right? If it's for the other ones in blue, yeah, part of calculating of a non-normal distribution. So then again, the median will be more accurate. That's why they actually compare the medians here. So for ANOVAs, there's also one-way or two-way ANOVAs. So basically, a one-way ANOVA has one continuous response variable. Remember, again, continuous data is numerical data. So for example, in this case, the one-way ANOVA, you have one continuous variable, which is a test score, and you compare the test score with three or more levels of the variable factors. So let's say in this example would be level of education. So you can see then in this graph, there's like college degree, graduate degree, and high school, and then based on this level of education, you try to compare their test scores. For a two-way ANOVA, so two-way means that there are two different variables. Two different variables you're testing. So basically, on top of level of education, you also are looking at the zodiac sign, for example. So here you have these two on the graph, and then you look at their test scores as well. Then what is ANCOVA? ANCOVA is basically analysis of covariance. It's like ANOVA, but then there's you're adjusting it for one or more continuous variables or covariates. So for in this example, remember before that we were looking at the level of education and then the test scores, right? So then, because if you think about it, then there are definitely other covariates or like confounders, right? So like things like number of hours spent studying, which is not reflected. And then based on this covariate, you try to adjust this, and then you use ANCOVA to adjust for it. MANOVA is multivariate analysis of variance. It's like a ANOVA, but it has additional continuous variable. So again, just now we talked about one way or two way, right? Actually, way is just factors lah. So here is the way I see is yeah, way just means factor. So in the first case, if it's a one-way MANOVA, you only have one factor to look at, which is the level of education. And then based on that, you want to see the different outcome variables. So for example, you want to see what the level of education can affect, how it can affect the annual income, and how it can affect the student loan debt. It's a two-way MANOVA. So you think you're talking about two factors. So in addition to level of education, you want to see whether gender itself will affect the annual income and the student debt. For MANCOVA, multivariate analysis of covariance, is also similar to a MANOVA, but it has one or more covariates. So again, the covariates will be the things that you are trying to adjust for, sort of like confounders. So again, there's also one way and two way. Again, way equals to factor. So in the one way MANCOVA, you have just one factor, level of education, and then you want to look at annual income and loan debt, but you also want to take into account a confounder, like you say, what maybe the patient has the person has a rich parents, right? So you don't know whether this one will affect the debt and the income or not. So this is one of the covariates you can be considering lah. For a two-factor one, again, there'll be two different factors. So in addition to level of education, you want to see whether the gender, how it affects. So this is the two-way MANCOVA. So on to the different graphs and used in statistics.
Keith, maybe we stop here for a while.
Okay.
So let's go through right. Okay. So I just wanted to summarize that, right? Actually, during the exams, they will not really ask you for the what is this test all about, but I think it's very useful to understand. Keith, you want to go back to your summary of your test? I think Keith has given us a very nice summary here. Because when we read at the statistical analysis part of all the articles, right, journal appraisal, then we always come across these, and we probably just read it as they are just words lah. So I think for all of you in future, I think it's good to every time when you read it, right, just go and revise about, okay, what is this PET test? Okay, did they really apply it correctly? So that it will eventually become like a second nature to you lah. You get what I mean? Because otherwise it will just appear as words. But to be fair, they will not really ask you exactly what is this or what is the definition and things like that. Probably I would think that, in a very in a very not a straightforward way, they will probably ask you about whether or not you think it's appropriate and why did they use this PET test. Then maybe that's one of the ways the examiner may set the question and ask you why do you think the author is using a PET test for this? Then you have to say that, oh, because this is a normal distribution and things like that. That's probably one of the ways they can apply can ask you during the exam setting. Okay, so we won't go through into detail how is this PET test done or things like that in your own time. I think it will be also good to actually go and read about how do they actually come to this your chi-square test, your t-test, and visual asset test, just the common ones. How do they actually put into the boxes, and how do they actually calculate this lah? Okay, so I will leave it to you all to actually read about this at your own free time. But the details of it, right, don't really have to pull your hair and fret over all these details of how the test is being done. Okay.
May I also make an exam comment that most times, right, the papers that are chosen for your exams, the test will probably have been correctly chosen. Okay, so it is very, very unlikely that you also be called on to comment whether this was a very appropriate test.
Correct. Because these are the statistician who do it. So I think, let's say if I'm going to set a question, I'll probably ask you something like, why did the author use a PET test? to assess you get what I mean? They will probably ask you why did the author choose a PET T test, for example. Then
Yeah,
you need to have
exactly.
some understanding about, okay, because it's a normal distribution, you're using category you're using a continuous variables over here and things like that lah. So these are straightforward, simple things that you need to kind of know about all these straightforward tests. Okay, can I just summarize this part about the statistical tests about it, and then Keith, you want to move on to your next few slides?
Okay.
All this ANOVA, all these kind of things, you kind of need to know how many variables are involved, and that's about it already. Okay, don't feel very stressed about it and they say, oh, I have to go and read into details and all this. Don't need lah, huh? Can
Okay.
Any questions? If not, then we'll move on to the common graphs that we will look at.
No question. Okay, then I move on to the graph lah. Okay, we start with a forest plot lah. So forest plot, very commonly seen usually used in meta-analysis. Basically, okay, I'll just go through how to read this forest.
Correct you forest plot doesn't usually see in meta-analysis. You see in many papers.
Oh, okay.
Okay, you just because in the forest plot with meta-analysis, it's just that the right hand side is not your subgroups. You can also have subgroups in like RCT. Then you go into subgroups and then you also have a forest plot.
Oh.
Okay. So but then now right is your variables on your left hand side where you have this one is in the meta-analysis are all the studies.
Oh, right.
Okay, so let's say I run an RCT, right? I want to look at subgroup analysis. I want to do it in the subgroup. Then here will be like, oh, maybe age more than 65, anemia, COPD, diabetes. And then I will see whether it favors like this therapy A or versus a therapy. That's also a forest plot.
Oh, okay. So
go through how to.
Okay. So usually in this vertical axis, it will be things like either if it's the meta-analysis, then it will be a list of studies lah. If it's like a RCT, like what Dr. Jennifer said, then it will be the other factors that you're looking at. And then the horizontal axis is usually the outcome. And then this can be either a odds ratio or risk ratio. It can be odds ratio or risk ratio. And then you look at the line in the middle. So this is the vertical line of no effect. So this means that there's no difference between the interventions if the line here crosses this vertical line. So if let's say the horizontal axis here is things like odds ratio or relative or risk ratio or relative risk, then the null effect value is 1 because you can logically, if it's 1, that means
if you want to use your mouse and point to them where the line of no effect and things like that,
here,
so
this
that
one
can follow you.
Okay, here. Wait, here. So this is the vertical line of no effect. So if you are using things like risk ratio or odds ratio, then the null effect will be a value of 1 because that means that there's no difference in the two interventions. Yeah. So then this box is the area of the box here. So you see each in this example it's a different study So each study itself, there's a box that's attributed to it. See all these boxes, and they are of different sizes and the size of the box is proportional to the weight of each study that's given. So if it's a very high powered study, very good study, then the box will be bigger So usually studies, how are they considered good? They usually studies with larger sample sizes and the estimates are more precise. So like tighter confidence intervals. So the horizontal line here represents the 95% confidence interval. So you want a shorter line. A shorter line means that the confidence intervals are tighter. If the line is so long like this, that means you're saying that then your 95 confidence interval has such a big range. So that's not so good. Then you all the way at the end, at the bottom, then there's a diamond, right? They're all squares here, then suddenly at the bottom is a diamond. And the diamond is basically to show you the overall outcome. So they sort of like take estimate of the average of all the different results. And then this is the one at the overall outcome. Yeah. So, and then the width, the horizontal width of the diamond is the 95% confidence interval for the overall result. Yeah. So any questions about forest plot?
Okay, so yeah, I'm ask questions. Okay, so Sujin, can you tell heterogeneity? Let's say this is for meta-analysis, okay? Actually, most of the time we use it for meta-analysis. Can you from the forest plot, like let's say you don't have the I squared over there, can you tell whether or not they are heterogeneous study or not heterogeneous study? How do you see that?
I guess if the result has skewed to one side.
Because if let's say this is a forest plot used in meta-analysis, how do you see whether or not the studies are generally heterogeneous or they are not heterogeneous?
I'm not very sure, sorry.
Nishini, do you know? Nishini not here. Chini is busy. Chini is not. Chini. Hello?
Chini is doing an ACT.
Oh, Nishini, why don't you tell them? You did the talk on the meta-analysis, right? On heterogeneity.
Okay,
Will you
so
be on the
okay, so you look at the p-value to test for presence of heterogeneity. If it's less than 10, then it's considered more homogeneous. If I remember, sorry, less than 0.1, then it's considered more homogeneous.
let's say you only have the graphs.
Oh, you
And
only
the
have the
graph
graph?
tell you, looking at the confidence intervals and overlap.
Then you look at whether it's skewed to one side, meaning if it's more favorable or less favorable, or if it's looking at odds ratio, then if it's more towards 0.5 or more towards 2. So which side of the line of null effect you're at. So then if it's all in one, more towards one side, then you will consider that the results are more heterogeneous. Sorry, more homogeneous. Yes, no?
And then yes, no.
Oh, sorry. I was trying to answer text. Yeah. Yes. Okay. So we are actually talking about when you don't have the I squared heterogeneity, right?
Yes, actually you have an eyeball test that you do for
Yes,
your
eyeball.
meta-analysis. So you actually look at the confidence interval whether they do overlap or not. If there's not a lot of overlap, because as in you see what I mean? All these lines, if they are not they don't have a lot of overlap, right? Let's say the line is here, the line is here, they don't have a lot of overlap. That means the studies are actually very heterogeneous. As
fact,
opposed to if let's say they're all like that, right? Then you will be more inclined to say that okay, the studies are generally more heterogeneous. This is an eyeball test for heterogeneity when you look at the forest plot in meta-analysis. Of course, when we talk about meta-analysis, we can look at other ways of looking at heterogeneity by looking at the statistical test, which is usually present at the forest plot. They will put it down here, but there's this thing called eyeball test when you look at the overlap of the confidence interval.
Actually, Keith, can you allow us to write on your screen? As in to write on the share screen?
How to do that, huh?
Oh.
You just write law.
No, because you know, if we can all write, then we can also draw on the screen.
Okay, can you do already? Can you do it?
Let me try. No. I think you have to give us permission to do it. Let me see. It's okay, never mind. Anyway, but
or you just use your cursor.
Maybe can you?
Anyway, what Jennifer was saying is actually something that we'll be covering a bit later, right? About accuracy and precision. Yeah, so it's actually kind of like what she mentioned about the eyeball test. Yeah.
Dr. Andy, you try again. I think it's allowed already. You can annotate on my screen. Are you able to annotate?
Oh.
There's an annotate button at the top.
Yeah. How come? Yes, okay, got it. Yeah. Thank you very much. Yeah. Okay. So yeah. Yeah, so sorry. Okay, so if everything is like all on one side, that's great. Okay, but if it was like this, then like this, or like this, then like this, then obviously it will fail the precision and accuracy test. Okay, yeah, but I think if you can quite confidently state about the I squared thing, I think that would be great. Most times, if the paper has something to do with that kind of heterogeneity, they would report it. Yeah. Okay. Yeah. So sorry. Good. Good with the annotate function now. Thanks.
So so basically you sorry, Dr. Jennifer, you're saying that the visual test, right? So basically you just want all the lines to be like one side, that would be the best, is it?
No, what I meant is the overlap of the confidence interval.
Ah,
If the
okay.
confidence intervals are overlapping, okay, it means it suggests that the studies are generally more heterogeneous as
Yes.
compared to if the confidence intervals do not overlap, then you are more inclined, it is more inclined to suggest that, right, the studies, right, could be more is probably the heterogeneity is probably higher.
Okay. Okay.
Okay,
Yeah.
so then
Okay.
of course you correlate and look at your I square and your tau and your p value lah.
Okay. Can.
Okay,
Okay. Can.
that's for meta-analysis.
Correct. Yes, and that one is actually a precision problem. Okay, precision. Yeah.
Okay. I move on to funnel plot. Okay. Can I clear the annotation? Let me see.
I think cannot
Okay.
clear already.
Can I? Okay.
Okay.
Okay. Okay. So funnel plot,
That's good.
a bit easier to. Okay. So basically for funnel plot, right, is to look for publication bias, and I'll go more about that later. But first we have to understand how to read a funnel plot, right? So the funnel plot is usually like that, It's like a pyramid like that. And each point on the graph, each dot here. Let me put my cursor. Wait, okay. Each
So
dot. Sorry. Hello. Hello. Can you hear me?
why do we want to look at funnel plot? Why? What
Ah,
are we looking for in
we
funnel
are
plot?
looking for publication bias.
Okay, we're looking
Ah.
for publication bias.
Okay, so before I talk about that, I will just explain what this graph means. So there are many dots. Each dot here is basically one study. And basically the larger studies with larger sample sizes tend to be closer to the top of this pyramid. Because they are more, there's more data, and then the confidence interval is narrower, tend to be a bit better in terms of the result, so they'll be towards the top. Whereas the smaller studies with smaller sample sizes, they usually more towards the bottom of the pyramid. Okay, and this is the so this is the overall effect in the middle with the 95% confidence interval roughly making up the sides of the pyramid. Okay, so you can see from this that if there is a publication bias, there will be asymmetry at the bottom of this funnel plot. Because how come there are no dots here? Usually if it's a well I say if there's no publication bias, then you should publish all the different results, right? All the different studies. Then there probably should be some dots here as well, it should be more symmetrical, so if there's nothing here, then you are wondering that, is there missing data? Did they purposely not include this kind of results at this area to make the overall study look nicer, Yeah. So so that's basically for funnel plot, to see whether there's any publication bias. Okay. Any questions? Don't have. I move on. So I move on to correlation. So correlation, what is correlation? Correlation basically assesses the strength of the relationship between two variables, and whether they have an association. So X here usually is the independent variable and Y is the dependent variable. So how you are trying to see whether this X thing, how much it affects Y. Okay, so if there's a positive correlation, Y goes up as X increases, like that. If it's a negative correlation, then it's the other way around, right? And if it's a zero correlation, means the data is all over the place. Then you can't determine any association. So it also basically shows the strength of the relationship between the two variables lah. So again, if it's a positive correlation and it's very strong, the data will be quite nicely lined towards the middle like that, in one straight line up like that. Okay, if it's a positive correlation but it's quite a weak correlation, then you'll see that the data will fly a bit here and there lah. It won't be so nice on the middle line like that. Or no correlation, again, the data is all over the place. And it's a negative correlation, is the other way around. Okay, the number here, the correlation coefficient, is always between -1 to 1. So the correlation coefficient, or otherwise sometimes it's written as R, is from -1 to 1. If R is 0, then there's no correlation. So the closer the number R is to 0, logically, then it means that the correlation is weaker lah. Whereas if the closer the value of R is to -1 or 1, the stronger the correlation. Right? If R is -1 or 1, then the line will be straight and all the dots will be on the line lah, which is probably is the ideal scenario lah. So actually, as long as R is less than -0.5 or more than 0.5, is actually quite regarded as quite a strong association already. And once again, correlation coefficient describes association, it doesn't describe causality. For regression, more on regression. So regression basically expresses the relationship of two or more variables in the form of an equation. So for example, this graph here, you are trying to see whether income is related to happiness. So you can see there's a value lah. Basically, from the regression analysis, you calculate a value. So y equals to y is a happiness. Happiness is 0.2 times plus 0.71 of x lah. So basically, you get the data and you sort of plot it on the graph, and then you can find out how much the happiness score is lah. It's always an equation of the x here. Yeah. So it can be represented by a line, and using the equation, it also has a predictive value, but does not talk about causality lah. And there are different types of regression analysis. We have a simple linear or univariate regression. You have multilinear or multivariable regression. You have logistic regression, and you have proportional Cox regression. So the types of regression the simple linear, basically this describes the linear relationship between a dependent variable and independent variable, so x and y. A multiple linear regression will have two or more independent variables. The independent variables can be either continuous, which is numerical, or categorical or non-numerical variables. A simple linear regression assumes that the outcome is continuous. So I go back to the previous slide. This is a simple linear regression. It's a continuous line up. So if you have logistic regression is when you have a binary outcome of interest. So for example, if you have the outcome of interest is just two values only, or is that a pass fail, yes, no, healthy, unhealthy, then you use a logistic regression. And proportional Cox regression is used to determine the influence of the different variables on survival. I'll talk about that later. So what's the difference between correlation and regression? So they both sound pretty similar, right? But actually there are some differences. So correlation is to see whether there's a quick and simple summary of these two variables and how they affect each other, either positive or negative correlation. Regression, on the other hand, is to predict a response from X. So you know that you have variables of money and income, then you want to predict how the income will affect happiness. Then you use a regression model to kind of calculate and get the number. Yeah. So the differences, I put it in pink. So the differences between the two, for example, for X and Y being interchangeable, yes, because no correlation, you're just talking about two things affecting each other, right? But regression, you have a fixed X, and then the Y itself is the one that changes. So you can't change the X and Y like that. Okay. Yeah, and then equation for yes for regression, and regression also can sort of predict and optimize the result based on your X. So you sort of can calculate the Y. For cause and effect, both they don't really prove causality, but at least, for regression, you can sort of use the calculation to establish maybe there is a cause and effect. So I move on to the last part about Cox proportional hazards. So basically, before we talk about that, we need to talk about survival studies. And so before that, I'll talk about prognostic studies. So what are prognostic studies? Prognostic studies, basically, they look at the characteristic of the patient. So the prognostic factors that can predict the outcomes and the likelihood of the different outcomes. So for example, they will get all the patients with a disease, then they study whether the patients with this factor versus this factor and how it affects the outcome. So prognostic studies give us a different value. So you can get absolute risk, like the 5-year survival rate. You can get a relative risk from the prognostic factor, whether this will how much the relative risk it confers. You can get a survival curve based on this prognostic studies. And you can also get the precision confidence limits to see how what's the 95% confidence interval for the survival. So survival analysis is basically you are trying to find out the time between entering the study and the occurrence of the event. So usually it's applied to data from cohort studies. And traditionally it was meant to get information on time to death in fatal conditions, but it also can apply to many other outcomes, not just death itself. But traditionally it was death, that's why they call it survival analysis. So actually, there are many problems with analyzing such data, right? Because, for example, the subjects might not have entered the study at the same time. So if the observation period is differs, right, then there might be differences in the data, of course, and survival data. Or the subjects just left the study early or lost to follow up. So these are called censored observations. So a survival curve will be used to calculate the median survival time instead of mean. So because they are missing data here, right? There are things like unequal periods and censored observations that people lost to follow up. So because of that, you can't calculate a mean, right? The mean, you don't have all the data, so it's a bit hard to get the mean. So instead, you get the median survival time. So very important concept is that the survival curve is used to calculate the median survival time. So what is the median survival time? It's the time from the start of the study that coincides with 50% probability of survival. So again, median, right? Median, mode, and mean, right? So median is the 50% part of all the data. So similarly, a median survival time will be how many people at from the start of the study still survive at the 50% point of time. Yeah. So it's the time taken for 50% of the subjects to have still be alive, basically. Yeah, and this value actually gives you comes to a p-value and 95% confidence interval. So for example, right, in cancer studies, most of the survival analysis will use the following methods. They can have a Kaplan-Meier graph to show the survival curve. The log-rank test would be to compare the survival curves of 2 or more groups, and then you have the Cox proportional hazards regression to describe the effect of the certain variables on the survivability. Yeah. So the Kaplan-Meier and the log-rank will be one variable only, whereas the Cox proportional hazards will have multi-variables. So I talk about the Kaplan-Meier curve first, right? So the Kaplan-Meier curve, right, it looks at the event rates over the whole study period, not just a specific point in time. And it's used to determine the survival probabilities and the proportions of people surviving, and it estimates the cumulative survival probability. So I'll just go through this graph here. So it's a very typical Kaplan-Meier curve. Okay, you have on the y-axis you have a percentage survival, and then the x-axis is the time. Okay, so a tick here again is the censoring. So either the patient here lost to follow up dropped out. Also, these are the different points on the graph are the censored data. A downward step usually means that there's an event that occurred. So usually probably a death. So in that whole group of patients that they were studying all the way here, then someone died. So the graph dropped. Yeah. And then the median survival time, you look at 50%. So percentage survival here. So you draw all the way across from the 50%, right? All the way here. Then you find out. So for example, for here, it will be 0.7 years is the median survival time, because at 0.7 years, 50% of people still survive. And then you can also calculate the survival probability, because basically you can give a value. Like, let's say you want to talk about survival probability at 1 year, right? Then you just go up the graph here, and then okay, 1 year, at 1 year the survival probability is about 20%. Yeah, so basically the censored, right? So data that people have dropped out of the analysis, or like didn't follow up, they are all called censored data, right? But they do not affect the graph itself. Okay, so the graph will still go straight all the way, and they will just put a line here to show that there are people who dropped out, but it doesn't change the height of the graph. Okay, yeah, it only goes down when there's an event that occurs, because you're talking about survival. Also, you assume that people who dropped out still survive, just that they are assumed to have the same survival prospects. So you only drop down when there's an event that happens, that someone died. So again, it can be used to calculate median survival time. You can see here, median survival time will be at the 50% mark. Then you just find out what's the value here in terms of years. Then survival probability at any given time point. Yeah. So again, now we go to the log rank test. So log rank test, right? Basically, you are just using a log rank test to compare two or more survival curves. So if you want to compare two or more survival curves, right? You can compare the two curves is you can get the population of people surviving at, let's say, 1 month mark. Then you just compare the two curves and you just get the value But however, if you do this, it doesn't reflect the total survival of the group itself, like the whole period of time you're analyzing. So that's why you use a log rank test. The log rank test actually takes into account the whole entire follow-up period. This is a significant test, and it helps to decide whether to accept the null hypothesis that there's no difference in the survival between the two groups. So log rank test, right, is actually the most widely used non-normal test of comparing two or more survival curves. Okay, so it's called a log rank test because the data is ranked first, and then they're compared with the observations and expected outcomes in each of the groups. It's used to test whether the difference between the survival times of the two groups is statistically significant or not. Okay, so for example, this in the log rank test, they always give you a p-value, or the log rank test will always have a p-value to show whether this is significant or not. And then you have a survival curve, and then for example, for this is like you look at lymph node metastasis Also, so I mean, logically, you know that if there's metastasis, then the survival will be affected more, right? Yeah. So the 0 is no metastasis, and the 1 is people with metastasis. Yeah. So you're trying to see whether, and this log rank test shows that there is a statistically significant survival difference between the two groups. The different small vertical lines here again are the censored data, data that's lost. So the last one will be the Cox proportional hazards, right? So the Cox proportional hazards, basically, before I talk about that, we need to talk about hazard rate. Hazard rate and hazard ratio. So what's the difference? Hazard rate is the probability of the endpoint at the time divided by the duration of the time interval. So again, the hazard rate. So the probability of the endpoint event, let's say death, divided by how long it took for the death to happen. So that's the hazard rate. The ratio, on the other hand, will compare the two hazard rates. So the ratio compares rates in the experimental arm divided by the rate of in the control arm, and the hazard ratio has a p-value and confidence intervals. So the hazard ratio, if it's 1, the two arms have the equal hazard rate. The hazard ratio is more than 1, then again, because here you are dividing, the experimental arm is at the top and the control arm is at the bottom. So it's more than 1. Clearly, it shows that the experimental arm has a more increased hazard, and if it's less than 1, it's the other way around. So I think a common concept here and a common question I asked in the exam is what's the difference between a hazard ratio and a relative risk, right? Yeah. So basically the difference is that it's quite similar, but the difference is that hazard ratio compares the hazard throughout the study, whereas the relative risk only looks at everything at the end of the study. Yeah, at one point in time at the end. Yeah, so you use the Cox proportional hazards regression basically to get the hazard ratio lah. And the regression model is actually to investigate the association between the survival time and one of more predictive values. It's basically like a log rank test, but you have more variables you're accounting for, and yeah, it adjusts for the effects. Yeah, so basically you can estimate the hazard risk from given the different variables. So a few principles about the Cox model is that the hazard curves are proportional and they can't cross each other lah. Yeah, and why the Cox proportional hazards model is called a proportional hazards model is because the hazard event is a constant multiple of the hazard in any other group. Yes, does that make sense? That's a bit chim, but anyone has anything to say?
Keith, you got example of a non-proportional kind of thing, or you relate it to what kind of diseases is suitable or to use a Cox proportional for that outcome. For example, like I don't know, is there anything that you can think that we cannot apply Cox to?
Are you talking about this one?
Yeah, or maybe there are some diseases that happen more at the early age, and maybe at the later age also more prevalent. Then maybe the risk over time is not the same. Maybe I'm just trying to explain that the proportional hazards also has to have some biological basis. If the disease is known that or the outcome is known to vary across time or disease severity or the outcomes that you're testing, then if biologically you know that they are not going to be proportional already, and then maybe the Cox may not be the best model. I think either Su Jun or Wan Chen did propose a different type of regression analysis that is not using Cox on one of their papers before, but I forgot the name of that. I'm not sure whether was it Su Jun or Wan Chen who presented previously a different type of survival analysis that is a regression form, but it's not using Cox. Okay, but if you don't get it, then it's okay. You can skip.
Okay, so if I may, so that's actually quite a good example. There's some conditions where it may not be proportional. So for example, I'm thinking about those that have bimodal peaks in life. For example, some autoimmune diseases and okay, let's say myasthenia gravis. Okay, and then right, yes, there are actually Cox non-proportional hazard models, but there are also non-Cox non-proportional hazard models. There are actually quite a lot of options out there. Okay, it's just that the Cox proportional one is the one that is our go-to, because most conditions do tend to have this like proportional sort of relationship. Okay, but I must admit, I think in exams it rarely comes out, but this is your argument that there are certain conditions where it's not proportional. And then in the non-proportional cases, we just have to use a different model. Okay, yeah. Sorry, something wrong with my camera, so I'll just flip it up. I'll see whether I can, yeah.
Is it true to say that like a genetic condition, then you can't really use a Cox proportional hazards?
No, not necessarily. It really depends on the disease, because there are some genetic conditions like, let's say, muscular dystrophy, right, where it is proportional and the time span is quite clear. Okay, but there are some where there are bimodal peaks in life. The example that I gave just now was myasthenia gravis. Okay, yeah, I'm sure there are quite a few more other conditions. So if it's myasthenia gravis, there's a sudden peak, in the 20s, 30s, and 40s, and then there's a second peak later in life, like 60s, 70s. So if you were to follow that over such a long period, you might find that it's no longer proportional. Okay. Yeah. Okay, no, my camera seems to be working now. Okay. Okay, so Keith, is that all?
Yeah, that's all.
Okay, shall we go on to the next presentation? Yeah, thank you very much. Yeah. Okay, who's next?
I will present my
Okay, Wan Chen, yeah. Okay,
one.
go ahead, yeah.
Okay, so while Wan Chen is trying to set up her section, right? Can I just remind In Yi and Su Jin, have you all start preparing your slides? Okay, never mind. Wan Chen can start first. They will talk. They will tell me later on.
Okay. Okay, so I'll be covering a few of the all these topics on hypothesis, null hypothesis, type 1, type 2 error, power study, alpha and beta level, and confidence interval and p-value. So basically, null hypothesis states defined by there's any difference observed in the result of two or more groups is due to chance, and the null hypothesis is important because it underpins the statistical test. However, the null hypothesis is rarely stated in clinical papers and should not be confused with the primary hypothesis. And this is one of the this diagram actually to illustrate basically to the. So basically, when the researchers wanted to do an experiment, then they have the result. They will assume that any difference is due to chance, which is the null hypothesis. After that, they will calculate the probability, and they will either accept or reject the null hypothesis based on the alpha level. And on the other hand, the alternative hypothesis, which means that there is a difference. In other words, there's a relationship between the treatment and risk factors and the outcome. Hypothesis cannot be proven true. It can only fail to reject alternative hypothesis or reject a null hypothesis. So type 1 error is actually a false positive result or wrongful rejection of the null hypothesis. And usually is attributable to bias, confounding factors, or multiple hypothesis testing, like data dredging, and then alpha level is a probability of a type 1 error. And so a type 1 error occurs when the null hypothesis, So this is to illustrate, basically alpha level is a threshold, and usually is set to at 0.05. So any value beyond this, I mean lower than 0.05, the result is unlikely to be explained by chance. On another hand, any result more than 0.05 is likely to be explained by chance. So if alpha level of is set as 0.05, the researchers stating that any observations with p-level of less than 0.05 are a positive result. And however, if the null hypothesis turns out to be actually true, which is the result below alpha, which means that the result below alpha would be a false positive result. And therefore, if a null hypothesis is true, the risk of making a type 1 error is equal to alpha. And type 2 error is actually a false negative result, meaning a wrongful acceptance of the null hypothesis. And type 2 error usually happen because of the sample size is too small and or the measurement variance is too large. The possibility of a type 2 error should be considered when every non-significant finding. And beta is actually the probability of making a type 2 error. And usually the level is arbitrarily set at 0.2. So if the null hypothesis turn out to be actually false, and only the result below alpha would be correct, which is the true positive, then if the null hypothesis is false, then the risk of making a type 2 error is denoted by beta, which is equal to 1 minus alpha. P-value is actually the probability of...
So which one is more serious, a type 1 or a type 2 error? Ask Lip Hong.
Sorry, what is your question, Dr. Jennifer?
Okay. Lip Hong, which one is more serious, a type 1 or a type 2 error?
Type 1, right?
Why?
I read this before already, but I can't remember. Let me see.
When someone, what we want to tell them?
If there is no, as in, if so, type 1 is actually a false positive result. If there's no difference, and your result showed that there's difference, I suppose, yeah, it's just more, yeah, I don't know how to explain it another way.
So
Say
which
that
one is more serious?
I think type 1 is actually, can we comment that which one is more serious? Actually, both can affect you, I mean, your clinical decision, and says that if there's no significant so supposedly there's no significant difference, and if your result, your new drug show that there's a significant finding, which is a wrong result, I think it is serious. Yeah.
I'm a bit confused.
Sorry, I don't know what's the answer.
I also don't know how to explain. Then you want to you want to explain to them? Ask to unmute again.
Okay. Yeah. So that was actually quite a tricky question, because I was trying to figure out how would I answer that. Yeah, because it really depends on the situation and what's the magnitude of the error. Both are equally bad, actually, and it depends also right on the condition that we are trying to uncover. For example, if it's a very, very serious condition, right, then the risk of rejecting a null hypothesis where the treatment is very good is actually worse than not correctly than not accepting it than accepting it. You get what I mean? So it really depends on the situation.
So I think I will. That's why I wanted to. I would think the correct answer. It depends on the hypothesis of the author. It depends on the hypothesis of the author and what the author is trying to find. But I would think that, right, if you are looking at most of the intervention trials, where we are looking at whether drug A versus drug B or intervention A versus intervention B, right? I would think a type 1 error in such cases, where usually the null hypothesis is there are no difference, would be more dangerous, because if you actually because type 1 error is basically a systematic error, right? Because there's a methodology problem, there's a recruitment problem, and all these kind of things. Whereas type 2 error is when there's actually a difference, but you can't find it lah. So maybe intervention A and intervention B, intervention A may be actually better than intervention B, but you can't find it. So you're not really causing any harm. Right? But rather if let's say intervention A versus intervention B, and then you committed a type 1 error because of a methodology, and then you actually find a difference, okay, then it could potentially be very harmful to the patient, because this is a
You will use that
methodology
result.
problem.
Yeah,
Yeah,
and
that's
then
a
you'll use the
yes,
result.
correct. Whereas the type 2 error is actually there is a difference, but you cannot find it lah. Means that you are just not good enough to find it. Then you just have to conduct more studies and see.
Correct. And
Yeah.
that also means though, of course, the flip side is that you're stuck with current therapy.
Correct.
And
Which
yeah,
may not be worse
may
off
not-
than what
yeah.
if you're not causing more harm to the patient than what is.
Correct.
That is what I would think that, you know, when you are applying to more of our day-to-day work, where we are really looking at intervention and drug trials lah, okay? But of course, the correct answer is, of course, you need to look at the hypothesis of the author and what exactly they are finding. You can't use this and blanket rule and then put it to all other studies, because some of them are not drug studies, they can be a diagnostic study or whatever. Oh, okay.
Yeah.
By the way, I know we are overrunning already, but I have a small interesting point, because I always mix type 1 and type 2 errors up. So I don't know whether any of you can actually remember it. So this is how I remember it, okay? Remember type 1 respiratory failure is hypoxemia, right? So I remember it as wrongful rejection of oxygen. So it's wrongful rejection. Whereas type 2 respiratory failure, right, is too much carbon dioxide, right? So it's actually wrongful acceptance of carbon dioxide. Okay, that's how I remember it. Okay, in case it will help anybody.
Okay, thank you. So p-value is the probability of getting the observed result by chance. As the p-value becomes smaller, the result are less likely to have occurred by chance, and therefore less compatible with the null hypothesis. Eventually, the p-value is so small that it is below alpha, and the null hypothesis can be rejected, which means that the result is statistically significant, or the alternative hypothesis, which states that the result is not due to chance, is accepted. So yeah, so basically if p-value of less than 0.05, which means that there is a to explain this.
You need to explain this during exam, okay? This is important things that you all need to get your words and your structure of a sentence correct.
Okay, so usually we set the alpha level at 0.05, and any value below that, which is less than 0.05, we usually we call it statistically significant, which is the p-value. Yeah, then difficult. So okay, if p-value less than 0.05 means that it is less than 1 in 20 of chance that it is sorry, figure. Wait, if alpha level is 0.05, the null hypothesis is rejected, which means that the results are statistically significant. Then, so meaning that there is evidence of association between variable and outcome. However, if p-value of equal to more than 0.05, which means that and if the alpha value is set at 0.05, the null hypothesis is accepted, then the result and statistically non-significant, which means that there is association between variable and outcome are not proven. This is just to summarize what had been mentioned, which is study between two groups, then you should have the result and see whether any difference in the result and whether the null hypothesis is accepted or rejected. Then you look at any type 1 or type 2 error. Yeah, this is another table to summarize what had been mentioned. If the null hypothesis is true and your test result, however, your test result showed that it is significant, it means that you are making a type 1 error. In other words, if your null hypothesis is actually false and your test result showed that it's not significant, meaning you are making a type 2 error. So next, probability that that a type 2 error will not be made. So basically power, it means that the probability that the type 2 error will not be made in the study, and it is to measure a measure of the study ability to detect the smallest possible difference between the group, and that is considered clinically worthwhile is if such a difference exists. The larger the sample size of a study, the more power of the study is said to have. And the value of the power ranges from 0 to 1. A power of 0.8 is generally accepted as being adequate in most research studies. And if inadequate sample size, it means that the study is underpowered and it fails to detect even large treatment effects. Yeah, in new clinical fields, pilot studies might be carried out to estimate the difference in outcome between experimental and control groups to inform a power calculation. So in conclusion, so basically the higher the sample size, then it will lead to better, improve the power. And if there is higher the difference between the groups or higher the effect size, then it will lead to higher power. And otherwise, the increase in precision of result, which means that the reduce in standard deviation, it also leads to higher power. Next, I'm going to talk about this one-tailed test. One-tailed test, basically it means that there's only one direction of interest, and the alpha level is set to test statistical significance in one direction, and the possibility that the result may be in opposite direction is disregarded. And two-tailed test basically means that there are two directions of interest. The alpha level is split between the upper and lower tails to test statistical significance in two directions. And the possibility of results in either direction is acknowledged. Yeah. So basically to compare with a two-tailed test, a one-tailed test has more power to detect a difference in one direction because it disregards the other direction. However, most analysts use a two-tailed test because the researchers are not sure in which direction the results will be. And a one-tailed test usually will be used only if a result in one direction is not possible or can be disregarded. Next, clinical significance. Statistical significance, as shown by the p-values, is not the same as clinical significance. Statistical significance judges whether treatment effects are explicable as chance finding, and clinical significance assesses whether the treatment effects are worthwhile in real life. Small improvements that are statistically significant might not result in any meaningful improvement clinically. Lastly, the confidence intervals and significance. So a significant result can be deduced by comparing the confidence interval associated with the summary statistic from two groups. Confidence interval is normally the range of values around a summary statistic in which we are 95% sure that the population summary the population summary statistic lies. And when comparing two groups, if the confidence intervals do not overlap, this is equivalent to a significant result. If the confidence intervals overlap, but one summary statistic is not within the confidence interval of the other, the result might be significant. If the confidence interval overlap and the summary statistic are within the confidence interval of the other, then the result is not significant.
Manchana, so you read out all these things on the slide. Can you tell us an example or give me a pictorial explanation? I don't understand why. It's the confidence in you ask them whether they understand. You understand what you have read out?
I was trying.
Yeah. What is summary statistics?
So basically, we have we collected all the data, and if the range of all the values that we have lies within I
don't know what is summary statistic. What's the summary statistic? Is this your last slide, Wanchan?
Yeah.
This is your last slide.
I think second last slide. Yeah.
What's the last slide? Okay, you finish up first.
Yeah, if a sample result is absolute difference between two groups in a study, the value of zero difference is the value of the no effect, which means that the confidence interval includes zero. The study result is statistically non-significant. If the sample result is ratio between two groups in a study, example relative ratio, risk or odds ratio, the value of 1 is the value of no effect. If the confidence interval includes 1, the study result is statistically non-significant.
So what does this mean?
So actually, as what is stated here, if you are looking at
okay. So
let's
see whether they understand this. Okay. So if I have let's say drug A versus drug B. Okay. The I'm looking at improvement. Okay, let's say drug A versus drug B. I'm looking at improvement in stroke. Okay, so the intervention is drug A, comparator is drug B. Okay, outcome is prevention of stroke. Okay, and then the relative risk of stroke, the relative risk ratio of stroke is 0.7. Okay, and the confidence interval is between 0.6 to 0.95. How do you interpret that?
Which means that is statistically significant.
Okay, you ask Valerie to interpret. You ask Valerie to interpret because you teach, then they must understand, right? If not, then what's the point of having a lecture? Valerie, come you explain. So what does it mean?
Actually, I don't understand. So can you repeat the range?
No.
you have a drug A, intervention is drug A, comparator is drug B, your outcome is looking at outcome is stroke lah, okay? So your relative risk ratio, okay, when you of drug A compared to drug B in preventing a stroke, in the outcome of stroke, right, is 0.7, and your confidence interval is 0.6 to 0.95. How do you interpret this? Wei Liang, Valerie is post call.
For your example, you mentioned that the relative risk reduction is 0.75.
Risk ratio.
Relative risk ratio 0.75. So I guess drug A is
Okay, I give
more
you.
Can I try, Dr. Jeremy?
Okay, yeah.
So what's your question again? Relative risk ratio is
You're
0.
making me very confused, you know.
Is it
Okay.
drug A is 25% less than drug B, the risk?
The risk ratio.
The risk ratio.
So okay, so what is Wan Chen trying to tell you here in this slide? It doesn't cross 1, right?
I think it's statistically significance because the
Yes.
confidence interval is not cross 1.
Yes.
Okay.
Okay, so can E just, it doesn't cross 1, but because you're looking at, can you see my cursor, right? Risk ratio over here, right?
Oh.
Yeah. So if let's say it crosses 0, let's say 0.6 to 0.
Maybe let's say if the range is more, maybe 0.6 to 1.2, then it crossed 1, then
Yes,
it may not
then it's
significant.
statistically non-significant.
Is it correct?
Yes.
Yeah.
Yeah.
Yes.
Correct. Yes. Okay.
Yes.
But because you're looking at relative risk, but if let's say you are looking at absolute difference, okay, then you're looking at the difference of 0. You understand?
Yes.
Yeah. Does everybody understand or not? So you need to know what, when you look at the confidence interval, whether it causes 1 or causes 0, right? It depends on whether you're looking at absolute risk difference. That means your group A was risk of happening in group A minus risk of happening in group B, right? The absolute risk different versus a relative risk ratio, because ratio is a ratio, right? So no difference means a ratio of 1 because numerator over denominator is no difference ma. Okay, so which means that when you actually are being asked what does your confidence in let's say they ask you what does this mean, right? Let's say the result, then you need to know that it's not always what I'm trying to tell you, okay, in summary, is that you cannot just tell the examiner because the confidence intervals does not cross 1, then there is then hence the result is statistically significant. So you need to know whether this is a risk ratio or whether this is a absolute risk difference. Do you all get me right?
Yeah. Yes.
Okay. Okay. So you need to know that because we all say that we always memorize the sentence lah, huh? But then it's not about memory, it's understanding what are we measuring here? Is it a ratio or whether is it a risk difference? Okay. Can I? Okay. In the interest of time, yeah, this one. I don't understand this. You also don't understand. Maybe Ending can understand. Maybe Ending can help us. So I have a question
Thanks,
here.
always I kena.
Yeah, so okay, so what's the difference between a p-value and confidence interval? Since both of them can tell me that it's clinically significant, right? P-value just at 0.05 is still significant. Confidence interval, if I'm looking at risk ratio, causes not causing one means that it's statistically significant. So why do I need to have both? I just have one can already, ma. Right.
Yeah.
Why? Vincent, you tell me.
P-value provides a measure of the strength of an association, and confidence interval indicates the magnitude of an effect and probable clinical implication. And because it provides a range of possible values. For the true effect.
No, this is
What's the question again? Sorry. What's the question again?
What's the
P-value
difference between p-value versus confidence interval? They tell you the same thing. Then why do we need why the papers will report both? This is Andine's favorite question. Okay, every time Andine will ask this question.
Hey, it is, but it's a good point. Yeah. So how was the difference here?
P-value, the smaller the p-value, it means that if then
okay.
It's a strength. It tell you the strength of the association.
Okay, no, it doesn't. Okay, but but that's because the p-value, right, is actually very poorly defined, and I think I discussed it at length in one of my previous things. I'll see whether I can dig out the slides for all of you. Okay, but between the two, I would rather have the confidence interval, because it not only okay, remember we're talking about summary statistic, right? In a sense, right, the p-value is a summary. You only get one value, 0.05, 0.03, or whatever. The confidence interval, right, is actually a lot richer because you have, first of all, you know where the tendency lies, and then you also can see, right, how confident you are about the results being within that range of values. Okay, so it not only tells you where that central value is, it also tells you what the spread is like. So if you ask me, between the two, I would much rather have a confidence interval. Okay, I think that's the basic explanation, but actually the p-value is actually a lot more involved than that. Yeah, it is not just the chances of of getting this result that's by error, right, is less than 0.05% or whatever we usually state. I mean less than 0.05. It is not as simple as that. And the confidence interval, actually the explanation is actually a lot more complicated as well. Okay, yeah, but
Okay,
anyway,
this is very so my simple mind is this lah. Okay, so you know that when you actually do your study, what happens is that from a huge population, let's say from Singapore, you sample this little circle. Okay, this is your sample population. When you run your statistics on this population, your p-value, right, ties in with that population only. Okay, so your p-value less than 0.05 is your 5% chance that your result, right, happens by chance, which means that you reject the null hypothesis. So it's a very statistical way for you to reject or accept the null hypothesis. Okay, so whereas when you sample this population, you need to apply this to your whole population. That's when your confidence interval, 95% confidence interval lies in. And when you just write here, right, you bold it in red, you are 95% sure that the population summary statistics lies. And this is by the central limit theorem, right, that the sampling distribution of the sample mean, which means that whatever you have sampled, right, your result approaches a normal distribution in the bigger population. So your 95% confidence interval will tell you where the population mean actually lies. And if it does not cross 1 or 0, then it actually tells you that statistically significant in your population. Okay, and why this is more we prefer to know that is because, first of all, right, it is more representative of your population mean. Okay, and secondly, right, it also tells you the precision of your results. The narrower it is, it means that your results are actually more precise. Whereas your p-value just tell you whether you reject or accept the null hypothesis based on your statistics that you are looking at. Hello, can you hear me?
Yes.
Okay. Okay, so actually you bold it here lah. 95% sure the population summary statistic line lah. Okay, do you all understand already?
Yeah, and of
Okay,
course, there was the earlier
can.
question about what the summary statistic is, right? It's just the mean, or like the mean blood pressure is this,
Correct.
or yeah, which I think Wen you couldn't answer that one just now.
Because you actually just write everything with all. I also get very lost. What is all these words all about? Huh? Okay. So anyway, in the interest of time, I just wanted to summarize that. Right. Actually, can you go back to your previous slide? You really need to know how to explain power. You need to know what are the components that are actually required for sample size calculation. Okay. I'm not going through this with you on time. But you need to know what are the variables that you change to improve your power. What are your power being determined by? If your effect size are bigger, what do you want to do in order to improve your power or something like that? Okay. Okay, connection is bad. I cannot hear anybody.
No, I think nobody said anything.
Okay. Okay, any other questions? I think you all need to really know your power and sample size calculation and what are the components that are required and what are the things that will change each component now. Okay, so go and study and read about that.
Can I add something?
Yeah.
Okay, I think I got a common a misconception recently that I thought I got it more settled, that if your study result, right, is statistically significant already, right, and your power is under power, for example, your paper says that you're supposed to recruit 1,000 patients, but you only recruit maybe 800, but you got a statistically significant result already. Then actually at this point, it's also difficult to say that you want to increase your sample size as a limitation to the study, because the study already did not commit a type 2 error. In fact, the study...
Yeah, correct. So you cannot use that as one of the weakness of the study. You're absolutely right.
So I just wanted to highlight to everybody that power, if the study is a very positive study, that means either it is a reduction or a reduction in the treatment or the beneficial in the treatment. Either ways, if it's already statistically significant, you cannot use an underpowered study, even if it's underpowered, to say that it is a limitation to the study, because the definition of power is towards type 2 error, which is false negative and not a false positive. So if you've made a positive outcome already, increasing your power will not make it less likely to be wrong. Also, you will detect more positive stuff, whether is it false positive or true positive, but it is not in the true definition of a power a limitation. I'm not sure whether you all get it, because I only recently got it after Dr. Choi.
So what happened is that, okay, a type 2 error means that there's actually a difference, but you cannot find the difference. So if you're underpowered, that means your samples are not enough. You actually increase your sample size so that you can actually find the difference. But if you have difference, you have already found a difference already, right? That means drug A versus drug B. Drug A is better, okay? And you're underpowered, means that this is really a true study, very good study, very good result. Means that you just need a small number and then you already get a positive result. You increase your number, means that the result is sure going to be positive. The drug A is definitely going to be positive in drug B already. Make sense? Okay, straightforward.
Okay. Caveat to that one. It also depends on the magnitude of the change. Okay, so like for example,
the effect size, right?
If you're detecting a very small, a very big change, okay, it's positive. But if you detect a small change, a very small change, you will need to increase the power. Okay, but anyway, good point.
Okay, so since you're on it now, how do you find the effect size? Can I change the effect size as and when I want?
No, I think based on previous study as a reference.
Yeah. So you can't change your effect size as and when you want. Okay. So you have to decide based on your previous study, because you can, let's say you look at mortality. If mortality in all study, right, is just like 5%, then you go and take like the mortality as like 30 or 50%. Of course, you know, it's not going to be reasonable, right? Huh? Okay. Okay, that's all I have. Any other question? Okay, any other things, anything you want to add on or things like that? If not, then
no, nothing to add.
Okay.
Thanks, Wan Chen. Actually, it's quite easy to read words, difficult to understand the concept. Stats is, and I never studied econs or stats when I was in junior college, so this is very tough for me.
Okay. Where is Sue?
Me here. I'm here.
Okay.
How do I go to it then? Okay, so while Sue is doing it, right? Su Jin and who Su Jin and In Yi.
I just check. Are you all seeing my presenter's view or mine? Just a usual slide. It's a normal view.
An overview, right? Okay, thank you. That's nice. Hello?
Yeah, we can hear you.
Oh, okay. Hi. So today my session is the last slide. Okay, so discussion points for today. I'm just going to share what I have read on these 5 topics: accuracy and precision, repeatability versus reproducibility, incidence prevalence, normal and skew deviation, placebo and nocebo effect. If I'm not wrong, I think normal and skew distributions, I think Keefe already also mentioned about that as well. So let's start with accuracy versus precision. So I mean, we are quite familiar with these terms, and I'm sure most of us already know what is accuracy and what is precision. I'm just going to tell you a bit more. So I think if you can look at it here, there is accuracy and precision. Both are, they measure they are just referring the quality of measurement. So which means is that if we do a test and we measure something, and we are just going to see the quality to measure these accuracy and precision are the one referring to the quality of our test result or our measurement. So, but there are different. So if you can see here, this y-axis shows the precision. This is the x-ray axis shows the accuracy. So, so it's, let's say, right, if we do a test and we got the results, if we do the MAC test and then we measure how close this test result to the accepted value, and if we measure that the degree of closeness to the value, the accepted value, then it is called accuracy. So which means, in other words, the closer to the results that we obtain, the closer to the accepted value, then the more accurate the study result is. So if you see here on this x-axis, the result here, all the small dot line, small dark spots, they are all nearer to our target aims, but they are all nearer. So you can say that this is high accuracy because they are all nearer to the target aims. Whereas for the precision is the degree to which with an instruments of the process, if we do the test again and again, and then we get the same value. Let's say you do the test, the test is like 1, the second one is 1.1, the third one is 0.9. They are all around at the same, the first value. But I mean, they may not be near to our accepted normal value or accepted target results, but they are all, no matter how many times you do the test, you will get the
nearer to the previous result. That is called precisions. So these are the difference between precisions and then the accuracy. So if like most of the time we can use an example like a thermometer. If the thermometer outside the weather says that it is, let's say maybe thermometer says at 35 degrees Celsius, and then if actually this patient already is really have a 37.5 degrees Celsius, then in that case, this thermometer is accurate. Whereas, and if you use the same thermometer, you measure it again and again in a short period of time, and it shows the consistent that it near the result is almost the same to the previous one at 37.4, 37.3, 37.6. But in that case, you can say that this thermometer also register correctly, so it can be, you can say that this is more precise. Also, this thermometer is both accurate as well as precise, but not all tests are precise and not all tests are accurate. So this is what I explained just now, is the degree of closeness to the true value. We don't normally have the true value. We only have the accepted value in our practical life most of the time. And so there's something that we need to know about, like precision is the degree, the one that I already explained. And we can use the standard deviations to measure the precisions. That's why when we are reading the confidence interval, and then sometimes by looking at the confidence interval, you can see whether this result is precise or not precise. So if it is precise, you can say that, oh, this result it's precise. So it's you can see that it's statistically maybe significant, but it doesn't mean that this is a true result. It may be or may not be that it's not a true result. That's my understanding. And these are all the same. Then I want to add a bit about the systematic error. When I read, I saw that it says that systematic error reduces accuracy. So that's why we need to end. If you look at it this side, random error reduces precision. So what is the difference? So the difference is we need to know what is systematic error and what is random error. So systematic error, it is a consistent error made in a series of repetitive tests. So it's mainly, if you do the test again, it's more like the error is always the same. If you no matter how many times you test it, it is the same. It's like you are weighing yourself, and then the weighing machine shows that, okay, if you have a weighing machine, it always tell you like 0.5 or like 1 kg above your normal value. So even if you do, no matter how many times you go and weigh yourself, it always show you the same value, but even though it is not your true weight. So that's why it is called systematic error. And random error is just, it is a variable error. It occurs in a series of repetitive tests. It has no, it is just coming out randomly. So it says that if you have a systematic error, it reduces the accuracy. So it will never reach to it will never be, no matter how many times you do, it will never be close to the accepted value. So that's why it can reduce the accuracy. And if it is precision, is like if you have a random error, like you cannot really predict what's going to happen, then if there is, then it can reduce the precision. So so how can we so I think how can we measure this reduce these errors? So basically, if you so in the end, why do we need to know all these things? Because if let's say if we're doing a test, and if random error will be smaller if you use a more accurate instruments or measurements made in small fine increments, and more if you test again and again, it is more precise, then in that case the random error will be smaller, and then so it's like if you do the measurement again and again, you will get to know the quantity, the true value, and you can. This is how you are going to get the interpret it when you are doing the research. So the precision, sometimes the precision is, it depends on can be separated into two things. As I said earlier, can separate it into repeatability as well as a reproducibility. So what is repeatability? So it's the name itself says that it is when you do the test again and again, it is the variation arising from all the efforts, which means that if you do the same test, you are the one doing it, the instruments, the operator, and everything is, you keep everything constant and you do the same test. But even though you are repeating the same test, everything still constant, you will have, the result may never be the same. There is a small variation in each time you do the test. That is called repeatability. So reproducibility is that, okay, let's say if you are going to the same test, but the variation arising from the same measurement process, but different operator, different instruments, and then you can, if you do the test today, and then the next day another person do the test, and with another instruments, but the results are more or less like the same. It's called, this result can be reproducible after a certain period of time, something like this. Oops. Okay. So what is repeatability and reproducibility? As I said earlier, both are more or less the same, but it's just that in repeatability, you keep everything constant under identical conditions. And you do the test again and again, because the first and the second test, there will always be differences in the result may not be the same all the time. So that's why there is a variation, and the result that you get, it is called repeatability. Then whereas in reproducibility is that there is a variation, but because the instruments as well as the operator has changed already. So all these are saying the same thing. So if you want to investigate the repeatability of measurements, you should at least make 2 measurements per subject under the identical conditions, just to see how precise or how precise this test is, or how precise this measurement is. You can do this repeatability test as well as a reproducibility, whether how reproducible the result are. You can try different with different instruments or different operator at different time. Why do we need to do this? Because to quantify the agreement, because the objective is to quantify the agreement and the reliability of the measurements. Because whenever we use some test or measurement, we need to know how reliable these measurements are. And then that, because we already know that the first result and the second result, they may not be the same, but we need to see up to what extent are we going to say that this is still considered reliable measurements. And if I'm not wrong, there is also another section, so you can test by doing a lot of the testing to see how reliable this study is. But I don't think I'm talking about these things here. Okay, that's all that I understand for the repeatability and reproducibility. I can give you a very simple example that I have read. It says that, let's say you are going to do a small experiment, and you have to at least, okay, you are going to do that research or experiment. You must determine the percentage of acid in a sample of vinegars. Your task is to determine the percentage of acid in the sample of vinegar. And how are you going to do that? You're going to observe the volume of a sodium hydroxide solution required to neutralize that given volume of the vinegar. Then you are in a laboratory. So you do the first test and you get the one result. And then you are just a bit doubtful yourself. You need to, okay, I want to make sure that what I have done is correct. So you will do another test. You will do you are the one doing it, the same test in the same laboratory room, and you will test you will get another vinegar from the same bottle. Then you will use the sodium hydroxide solution to see whether what is the percentage of acid in this vinegar. Then you will get another result. So this is called repeatability. If I'm not wrong, yes, this is called repeatability. And you see whether within these two results, and then there should be an agreement to it, and see whether, okay, if let's say the first and second one, if the range is within this thing, then in that case, I would say that this is repeatable. This measurement is all right, or this measurement is within the agreement that we can accept. Then this kind of method can be used as a measurement in the future if we want to know how what is the sample of acid in this vinegar. So I think this is how it calls repeatability. Maybe if you change this test by another percent, I ask my friends to come and do it maybe the next time. Then if you do the same test, the same method, and if he also produced the same, more or less the same the result, and then if these two results, there is agreement to it, and you see that this one is also is within the agreement, then in that case, you can say these results are, this measurement is reproducible. You can use this kind of measurement in the with another percent and another conditions are. So that's what my understanding is for this precision, repeatability and reproducibility. So basic statistics, the reason why I'm going to talk about it, just a very brief one, because I think Keefe already talked about it. So whenever we have a sample, then the types of, if we had a sample data, then we need to, because all these sample data are supposed to convert it to the population, because these samples represent the population. So how are we going to know these samples are representing the populations? The data that we get, what are the types of data? How are we going to describe it, this data, and how are we going to use this sample data to make an inferences about the whole population? Well, here I'm just going to talk about this middle one, ways to describe the data, the types of distribution and measures of spread. So type of data, we already talked about it just now. So after data are collected, information needs to be organized and summarized. Then only we will know what data are we looking at it. So the type of data and scale used to measure. So these data and scales are to measure the variables. Variable means everything that we do. Like if we're studying the hair color, or if every variables that we are studying, it is used to measure the variables. Are important because after we look at all the data, we will decide what are the tests that we are going to do what method of data analysis are we going to use for the data samples that we have. So the type of data and some example, these are the ones that I talk about.
So sorry, I think you need to speed up a little bit, okay? Because it's a bit of, yeah, because we only have 10 more minutes left.
So I think we're done talking about the data. So we have a quantitative data, qualitative data, and as well as the epidemiological data, which I'm going to talk about incidence and prevalence. All of us know what is incidence and prevalence are. Incidence, these are the measure, these two are the epidemiological data to measure disease frequency in the populations. So this is the picture that we will see when you Google it. So like this is the prevalence of how much water in the sink, and this is the incidence, and this is the prevalence. So based on this picture, we can say that incidence is the number of new cases over a period of time. The only thing that picture doesn't show is the time, okay? Because we need a specifying time in order to talk about this incident prevalence. So incident number of new cases over a period of time divided by the population size, that is the incident rate. And the mortality rate is also a type of incident rate that expresses the risk of death in the population. Is also the same, but it is the mortality rate. And then the prevalence. So prevalence is also a number of people. When you do a measurement, when you go to one city and see how many diseases the prevalence of these certain diseases in that population at given time. At only in 2021 or 2020, then you will see that at that point in time, the number of people with the disease at a given time divided by population size, that is the prevalence. The same thing, period prevalence is almost all are the same. Lifetime prevalence also the same. So, okay, just to what are the clinical implications? Prevalence is the useful measure. It is to see the burden of the disease. So if you know that knowing about the prevalence of specific disease in certain area, we can just depending on the health service demands of the health services, we can just allocate our resources to those areas. And sometimes we always misunderstood that prevalence changes when people with the conditions are cured or done, which means sometimes we can just say, oh, higher prevalence. It doesn't mean higher prevalence doesn't mean that it is bad, because higher prevalence it only means sometimes a prolonged survival without cure, or maybe an increase of new cases, which means it's like a HIV. HIV, we see a lot of prevalence of HIV diseases nowadays, probably because the rate of death is now it's even lower. Because the rate of death is lower, even though the incident, the flow to the scene is at constant, probably because the outflow is lower now. That's why the prevalence will be increased. So that's why the only thing that we need to be aware that the higher prevalence doesn't mean it is bad. Sometimes maybe prolonged survival without actual cure, or maybe increased new cases of both. Lower prevalence means that more people are dying rather than being cured, or maybe if it is a very rapid recovery, like Ebola cases, like you will just see after a peak, you will just see the lower prevalence because almost all the patients die. So something like that. So, and then normal and skewed deviation, I think Keefe already talked about it just now. It's just to it is the probability of distribution. It is very important because when we get all the data, we need to plug it on the graph. If we plug all our data on this graph, and if you see the graph is like this bar shape, then you know that, oh, my data that we are getting is all normally distributed. Why it's important to have a normal distribution? Because it's easier to calculate. Because if it is a normal distribution, mean and median are all the same. And what else it means that, I mean, this is just the properties of the normal distribution. And then, so for the normal distribution, we can use the standard deviations to describe the extent of the data spread. And the larger the deviation, the greater the spread of the observation. Everything that we are looking at, the spread is wider. And it is, as I said earlier, then standard deviation, it is a measure of the precision also, and the standard deviations. So this we already talked about it. I will just skip. It just means that according to this rule, 60%. If you say one standard deviation under this curve, 60% of the data falls within one standard deviation of the mean. So why is it important? So if it is data are normally distributed, it's easier to perform. You can do a t-test, analysis of variant, parametric test, because these are why it is important, because these tests are more So if you can perform these tests easily, and then how do we know whether the data are normally distributed or not? You can just plot the data on the chart and checking it. You can just actually see it whether it is a bad curve or not, that it is a normal distribution. And skewed deviation, if it is not a non-normal data, can be summarized and by using median interquartile. The advantage is that median it is robust to outliers because it is not affected by the outlying points, which means because the median itself, the definition is that it's only at the 50% of the median value. So no matter how many outliers you have, if you look at this data, because median is here, you only talk about this two. No matter how many outliers you have, it doesn't affect the median value. So I mean, it will have some, it will have a effect on the data that the analysis that we did. So now we need to know about this. But there are a few distributions that the data distributions that we need to know. But out of these three, we need to know about normal distribution, positive skew, and negative skew deviation. Why it is positive skew? So we always think that positive skew is because we are looking at the peak. Actually, it's not. We are looking at the tail, because the tail belongs to because if you look at the x-exit, this side is the negative value, this side is the positive value. If you look at this tail here, the tails go on and on. If the tail is if going on this way, and if the curve is became not a bear curve anymore, then it is called a positively skewed deviation. And in that case, if you plot all the data, you see that your data, that the graph is skewing to this side. You can see it is positive skewed deviation, and in that case, mean is lower than the median, and you cannot use as a mean. You have to use the median. Mean is larger than the median, which is larger than the mode. So you cannot. Mean is not in the middle anymore. The same for the negative skewed deviations. And so there are only two things. Normal distribution, we use the measure of spread, we use by checking the standard deviation skew, interquadrant deviations, and the average measure, the average that we use is in normal distribution, we use the mean, and in skew is we use the median. So because it is powerful to analyze normal distributed data, then if let's say if your data are not normally distributed, you can use that logarithm transformation. That's why some of the research, they will just use this so that it will be easier for them to interpret. So placebo and nocebo effect. I think this is the last slide. So I mean, all of us know what is placebo effect and nocebo effect. It is something, placebo is something, it is an inert substance. It doesn't cause you anything, but it is usually, what is the placebo effect? It is the improvement seen in subjects when they are in receipt of the placebo treatment, which means they think that they have received something, and then there is an improvement seen in the clinical effect. So it is proven, and it says that even there is a lot of study, a few studies and research, and the reason why some of the research they wanted to, there are some research to look for why those patients who receive the placebo effect have actually, why do we actually see the clinical improvement? And they want to know what is the reason. So most of the time, the study that I search for, usually they say they want to look at the mechanism underlying it. So the nocebo is a different term. If you can see here, placebo, Latin word, I will do good. Nocebo is I will do harm. Some people, because they believe that they are receiving a bad, or like they are receiving an inferior substance to the good one, so they may have this thought that, okay, I'm not getting a proper treatment, I'm not getting the right treatment. Then because of their thoughts, they will have a bad effect. They will have a worse clinical outcomes. So why do we say that? There are a lot of studies who that really wants to look at the mechanism involved in placebo and in having this placebo and nocebo effect. There is this review article in NEJM back in 2020 that looked through the possible mechanisms, as well as how as a physician, how as the researchers can prevent or maybe like can control this placebo and nocebo effect. It is quite useful. When you read this NEJM, the article. So the mechanism, they say that it's quite, actually there is no certain or the evidence proven mechanism, if I'm not wrong. A lot of people are not very certain about it, but there are a few studies are saying maybe neurobiological mechanism, maybe because information offered in relation to the treatment, because whenever we give the patient medication, right, we just say, okay, this is a painkiller. Okay, this painkiller is supposed to relieve your pain. Then patient take it and they say, oh, I feel happy because I got this medication. Because that's why it is very important for us to give information every time we give a new medication. That's what it says. Then only it will affect. Because if you give the medication without telling the patient that you already received the paracetamol, they will still ask you for the paracetamol, the painkiller, because they don't know. And so it's something that information offered in relation to treatment. Patient expectation, they already expected that, oh, I'm receiving this medication and my headache will gonna be better in an hour time. So it may be because of that. Maybe patient may have a previous exposure. Because I've taken a paracetamol before, after I take the paracetamol, my pain is relieved. So they may have had a previous experience with regard to the drug or procedure, something like that. And then, so all these things can affect the placebo and nocebo effect. So how are we going to control it? Like how, not really control it, how are we going to, whenever we do a research, whenever we do a clinical trial, whenever we read the articles, or whenever we are dealing with the patient, how are we going to take this effect into consideration? So So it says there is the table, maybe in the laboratory, genetic or other investigation, assess if you're going to do a research, maybe assess the placebo nocebo effect into the appropriate control groups. And maybe sometimes you can even use a no intervention group, but it's not really possible all the time. This is for the laboratory, genetic and other investigation. And here, clinical trials. So clinical trials, you can ask the patient baseline so that when you are doing something, you will know whether they are, is it because of placebo effect or not. Ask patient baseline how much improvement they want to expect from this active treatment, or whether they believe they receive the active treatment, or these are the series of questions that you may need to think about it before you do the clinical trials. And clinical practice, it is actually quite relevant to us. Become familiar with the mechanism of placebo and nocebo. So mechanism of and then favor positive association. So that's why it's always good to build a rapport, let them understand what you are doing to them. Then if you can reduce this, if you can build up the positive association, then in that case, it will favor more of a placebo effect. So I think that's it's say in the NEGM how to implication of placebo and nocebo effects. These are the references I use. I think that's about it. Thank you.
Poor thing you have to rush through the last part. Actually, I like that image of the sink, the incidence and prevalence thing. I thought that actually summarized it quite well. Okay, did anybody have any questions? I know we've overrun quite a bit. Thank you for your patience. Okay, maybe I just one comment. It's very interesting that sometimes when we have skewed data, we really do try to apply those models and then push it back into a normal distribution. Yeah, like I think you mentioned, right? It's just that we have to also interpret those results with cautions, because if there's a skew, there's a reason there's a skew. Okay, now, and if the reason for the skew is because of the way we did the study, then it's reasonable to use those models to adjust it back. But if the reason for the skew is that really there are some cases that are more prevalent in that particular part of the population. I'll give you an example, like COVID. Okay, COVID deaths, right, is a skewed distribution when you look against age, let's say. Okay, so in that sense, the mathematical modeling may not be so useful as stratification. So instead of looking from age 5 to 95, we will just look maybe from age 70 to 95, and then maybe within that group, it is normally distributed. Or you can use the x-axis, right, as something else other than age. Okay, just to give you an example. Yeah, but there is a tendency for all of us to try to move towards a normal distribution, because then we can apply the all kinds of logarithmic regression and stuff like that. Okay, yeah, sorry, just my small point.
Okay, I ask you something about this repetibility and this
reproducibility.
I mean, how do we apply in our general credit scales, or maybe?
Okay. Yeah, so repeatability, as you correctly pointed out, is that you repeat the test many times. Reproducibility, right, doesn't necessarily mean that you have to do it many times, but it means that every time you do it, the result is the same. You get what I mean?
Is it the same as reliability? It's not the same, right?
No.
It's definitely not the same, but I don't know how is the connection between all these things.
Okay.
I try to search.
Okay, because they all have different names, right? They really do mean different things. Okay, so let me think of an example. Okay, let's say you have a test, an antigen rapid test, okay, something that we want to diagnose COVID with. Okay, so reproducibility is like, if let's say we have a slightly different, like 5 different test kits, but all of them always give the same result, then it's a reproducible result. Okay? But repeatability means that we use the same test kit like 5 times, and then let's say 4 times out of 5 or 5 times out of 5, they always give the same result. Then that's repeatability. Okay. Then for reliability, you see, whether the result is positive or not, it still may not be a true positive or true negative. So then reliability is that you do it a few times with that particular test, and then whether it's always consistent that the answer is a correct answer. Okay, so like let's say a brand A of antigen rapid test, but they only get the results right 20% of the time. Then you have brand B, they get the results right 90% of the time. Then brand B is more reliable. Okay, but it's got nothing to do with repeatability or reproducibility.
Can I ask, like, how do we need to, like, how do accuracy, precision, and error related to each other? The thing that I say, is it correct or is that wrong?
The target diagram that you drew, right, is actually very accurate, and that's the way that I also remember it. So you're referring to the text or to the picture? Because the picture is accurate. Yeah.
I mean, like, do we need to like relate each other? The accuracy.
Okay.
error?
Usually in the exam, I don't think they actually ask such specific raw data questions because you don't have access to that raw data. Okay. So we would tend to then just recommend that you avoid the words like accuracy and precision because they don't usually arise. And then the error, right, is I think is very straightforward. You just use the term error when it comes to like type 1 error, type 2 error, and maybe a standard error of the mean, if you know what that is. Otherwise, there's usually no need to mention these things in the actual exam. It is good for your own knowledge, like the target. I think it's a very nice picture, but it doesn't actually usually come up for exams. Okay.
Thank you.
Okay, but you know, just to answer your point, just in case, usually it refers to, let's say, a test kit. Okay, so as you quite correctly pointed out, the test kit, right, can always get the same answer that's precise, but the answer may be wrong, so it's inaccurate. Okay, whereas the yeah, so if you take an example of, let's say, a urine pregnancy test, that one might has to be highly accurate and also highly precise. Okay, it's a bit like sensitivity and specificity. You can have one or the other or both, but in certain cases, right, you need it. Any other examples? No, it's okay. Most tests that actually make it onto the market tend to be precise and accurate. Okay, because if not, it won't market well at all. Yeah. Okay, so yeah, so that's why I said that this something doesn't usually arise. Okay, were there any other sessions? Okay, I guess if not, thank you very much everybody for hanging on for so long. You have a look at the Dropbox link that I sent all of you. Okay, that might be helpful. Yeah, and if you have any questions about any of the resources there, do feel free to link up with me. Okay, or if you missed the link, then you let me know that I can send you the link again. Okay. Yeah. Okay. If there are no other questions, oh sorry.
Yeah. Okay. So anyway, thank you, the two of you. Okay, we only have left the last session, and I think from this session and next session, right, it's very statistic heavy and very information heavy. Okay. Can you all take offline and discuss among yourself whether you want to split the next session into two different session or you want one because the presenters may not have prepared the slides lah. He went to. Okay. So can you discuss offline and let us know early? And when you all give us the slides, can you give us a bit earlier, like almost one, the best is like 1 week earlier, so you can let us have 1 weekend to go and vet the slides and the information that you all gave us, because we also have to do time control. You all last minute add on a lot of slides, right? Then it overruns a lot, and then there's a lot of repetition because you all don't speak to each other, then we need to go and reconcile everything. So can you give us a little bit earlier, at least at best, the one weekend to look through, because if let's say we are busy for the rest of the Monday to Thursday, right, it's very hard for us to get the slides for you. Okay.
Can I suggest a good PowerPoint presentation skills? Every slide should have no more than 7 words. Okay? 7 words. So pictures are good. Pictures are really good. They really help. Yeah.
And for you all, right, why did I make you all to do all this, right? It's because I want you all to be able to understand the concept. So please, when you all go and read out and prepare your slides, it's also a good opportunity for you to revise and understand it. Meaning that, right, please don't read from the slides, okay? Because when you're reading from the slide, it means that you don't really understand. Your audience will not understand already, okay? So I want you to go and digest it so that you can put it into something that you can understand and explain to your audience. So even the audience don't understand, at least you have gotten your concepts very clear already. All right. So for the meta analysis, right, I think my friend was asking me, I'll try to arrange one session with Dr. Ravindra to go through how do we create a meta analysis. Okay. So I just want to stress that learning is all by yourself. Here, we are just really trying to facilitate. Okay, how much you all learn is really how much you all prepare and how much you all teach each other. Okay, so I won't hold out your time, so that it's Friday, everything go and exit. Thanks, Andin, for coming in.
No problem.
Do let us know so that I can book Andin early. Otherwise, you all will not be able to get him to teach you all this good statistic knowledge that he has.
Not that I'm that good.
Okay, so let us know early, preferably by next Monday, what are your consensus in terms of how you want to do the last session. Okay? All right, okay, thanks everyone. I will end the session here. Okay, bye-bye.
Thank you. Thank you.
Thank you. Bye-bye, everybody.
Bye-bye.
Thank you.